Welcome to Lawrence Tech, EGE 2013 Statics. I'm Jim, and today we're going to look at this beam with a distributed loading and a couple of supports, and we're going to be graphing the internal forces in that beam. The shear forces, bending moment, and, well, the normal forces are equal to zero, but we'll mention those. And I recommend that you pick up a pencil and paper and try to follow along with the math so that you get this thing cemented in your head. Now this one is quite a bit more complicated from the math standpoint than the previous one because of the way we've laid out the supports and the changes in loading, but you'll see that as we go along. On a previous video, we calculated the equivalent forces from the uniform portion, the triangular portion, and we calculated the reaction forces. So I'm not going to repeat that. I'll just put a link up here in the upper right corner so that you can go watch that video if you wish. But recall, if a beam is or any object is in equilibrium, when we cut a section out of it, that section has to be in equilibrium, and it will be held in equilibrium by internal forces. But by cutting that section, we essentially expose those internal forces, and we can use our equations of equilibrium to find what they are. A couple comments on sign conventions. I have drawn all of these reaction forces here in the positive direction for our convention for the internal forces. But if we're doing equations of equilibrium, we need to use the previous conventions where counterclockwise is positive, up is positive, and etc. And sometimes that convention can cause a little confusion. For example, if I was looking at this uh, segment to the right, I would look at it and say, well, this is a negative moment because it's clockwise when I'm calculating the equations of equilibrium. But when I plot the internal forces or internal moments in that beam, well, this is positive according to our internal forces convention. So we have to be a little bit careful with signs, okay? Because if you were to look at this beam as a whole, if the bending moment were positive all the way across, and we cut a section, we end up with moments in the direction they're drawn here, but it's positive on both sides, so it's drawn in the positive direction for an internal moment. But if we're doing equations of equilibrium for this beam, we would treat that like a negative moment because it's clockwise. The first step in this problem is to just essentially cut this up into manageable parts. And as I look at this drawing, I have a reaction force here. I have a reaction force here. Notice there's a change in my loading right there. And so that leads me to break things apart. If I take this section right here, I have a loading that's constant from one to the other, and that gives me a section that's easy to deal with there. From here to here, my loading it's not constant, but has a constant slope or constant equation. But I have this reaction force applied at a point in the middle, which is going to give me a discontinuity in my shear and a change in slope in my moment. So I'm going to actually divide, take a chunk out here, that's that section, and another chunk there, that's that section. And then finally, off on the end here, we have this little bit of beam sticking out where there's no forces on it at all. We'll deal with that last. Process will be simply to start at the left, and we'll solve the equations of equilibrium to find our internal forces as a function of distance in one section. Then we'll do the next section, and finally the last section. Let's start with our first section, which takes us from x equal to 0 to x equal to 10. I've drawn a free body diagram down here at the lower right. We have a reaction force here of 118.1 newtons. We have some force here, which magnitude and location we need to determine, shear force, and a moment that will be necessary to keep this in equilibrium. By inspection, we can see that the normal force is equal to 0. Assuming we cut a section on this beam at any arbitrary point, and this is at some distance x, we can find out what the magnitude and location of that force is, and from that we can find the normal or the shear and the moments. So if I just first calculate my force for the loading on a subsection here, I can convert that to a single equivalent force. My force equivalent is equal to this 20 newton meters, 20 newtons per meter loading times the distance x to that section, and the location will be at basically 1/2 x since it's a triangle. So to find the shear forces, we'll look at the sum of the forces in the y direction, which have to be equal to 0, and that's going to be equal to our 118.1, which is upward, minus our force from the rectangle, which is minus 20x, and minus our shear force, which we have shown drawn down, minus v, and I can solve for v, and I get equals 118.1, actually equals negative 118.1, plus 20 times x. I can calculate the necessary moment at that section by assuming that the sum of the moments at that section equals 0, and that's going to be equal to the moment from the reaction force to the left, which is minus 118.1 times x, and that's negative because it's taking us clockwise, plus 20 times x times our distance x over 2, and that's positive because relative to our section here, that's going to give us a counterclockwise moment, plus that counterclockwise moment we have drawn. And if I juggle the numbers here, I come up with my moment equals minus 10x squared plus 118.1 times x. I have equations for my shear and my moment as a function of the distance from the left edge, x, and I can plot those. I did it using MATLAB, and the equations you see up on the upper right. A couple things to note here. Our assumptions about this beam is that there's a pin here at the where the reaction forces are applied or where it's supported. So since it's a pin, there's no moment in that joint, so our moment starts at 0. There's a reaction force of 118.1, and so our shear starts at that 118.1 up here. It's a uniform rectangular loading, so we're subtracting total shear because it's counteracting that support reaction at a constant rate. So we have a constant negative slope here, okay, or a constant decreasing value is a better way to look at that. When we start out on the moment, we have a positive slope because these values here are all positive. And as we get closer, further and further out, the slope of the moment curve is decreasing because the magnitude of the shear curve is decreasing. When we cross a shear of 0, our slope in the moment is equal to 0, and then our shear goes negative, so the slope on the moment goes downward, and as the magnitude of the slope goes more and more negative, our slope, as the magnitude of the shear gets more and more negative, our slope goes more and more negative on the moment. And that's all consistent with the concept of the shear being the integral of the loading and the moment being the integral of the shear. When we move on to our next segment, we're adding this little bit of the triangle between where the triangle starts and where the support reaction is, which complicates it by not having it at the end, but we can work this out. And let me draw a picture here. If this is that triangular area at any position x, and this is 10 meters there, and that's 15 meters there, I can divide this up into a rectangle and a triangle. okay? And I can find the equivalent area or the equivalent force for each of those, and I can find the location where that's applied. The top of this triangle is 20, the bottom is 0, and this line which defines the end, we can determine the equation for that is 20, the initial value, minus 20 over 5, the slope, times x minus 10, which is the distance from the left edge. And on our free body diagram, we already know this is 118.1. We know that this force here is 200 newtons, and it's at a distance of 5 meters. And that's from that rectangular force that we already calculated and have moved beyond. There'll be some force from the rectangle and some force from the triangle at some location near the end of that beam, and we'll calculate the values of those triangular and rectangular components of the force, and then we can use that to solve our equations of equilibrium. So if we look at our rectangle, there's going to be a certain load from that rectangle, F sub r we'll call it, and that's going to be equal to the height of the rectangle, which is 20 minus 20 over 5 times x minus 10 from the equation of that line over there, times the width of the triangle, which is just x minus 10. And if I do the algebra, I end up with minus 4x squared plus 100x minus 600. And at this point, I would, encourage you to stop the recording and make sure you understand where all this stuff comes from, okay? If it's not immediately obvious to you, how did I come up with those numbers? Because you may have to do the same on an exam or, certainly on homework. And just hearing me say that doesn't help you really retain that unless you actually do it yourself. The location of that force, the equivalent force, if we break it down to single equivalent force, is going to be basically the middle of that rectangle. So the location of the rectangular force is equal to 10, which is the left edge, plus 1/2 of x minus 10, which is the distance from half the distance between 10 and x, and that's equal to x over 2 plus 5. For our triangle, force from the triangle equals, for a triangle, it's 1/2 the base, which is x minus 10, times the height, which is 20 over 5, times x minus 10, again from the equations of that line. And again, I would encourage you to work that out for yourself and make sure I got it right, because you know what? There's no guarantee I didn't make a mistake. And that's equal to 2x squared minus 40x plus 200. And the location is equal to 10 plus 1/3. Why did I write 1/2? 1/3 of x minus 10, and that's equal to x over 3 plus 20 over 3. So to find my shear forces, hopefully I don't run out of room here, I'm going to do the sum of the forces in the y direction equals 0. I get 118.1, that's our reaction force, minus 200, that's the force from that rectangle from before, minus the FR, so minus the force from the rectangle minus the force from the triangle plus our shear force V, which we have drawn upward, and I get my shear force V equals 2x squared minus 60x plus 318.1, and that's our shear. And our normal force, I'll do the sum of the moments. I'll do that over here on the right. Sum of the moments at our section equals 0. and that's equal to minus 118.1 times x, that's the moment from our reaction force, plus 200 times x minus 5. Again, stop the recording and figure that out if that's not obvious. Plus the force from the rectangle times the location of that force, plus the force from the triangle times the location of the triangle, plus our moment. Wow, just made it. This is kind of a messy one to multiply all this out. It's a fair amount of algebra, but you decide if you need to do it. So our moment equals, when I do multiply it out, 0.6667 x cubed minus 30 x squared plus 381 x minus 666.7. And again, we found all of these using our sign conventions for external forces and reactions, not for the internal forces. But it turns out I've got a positive moment drawn, and it corresponds with a positive moment in our clockwise counterclockwise convention for external forces. In another comment, I multiplied all these out to get a polynomial. The fact of the matter is, I could have, when I'm using a tool like MATLAB or whatever tool you're using to do the math for you, very often you could just enter the equation pretty much like that, where you've calculated FR and LR and FT and LT, and you don't have to keep re-entering the numbers, and there's less chance of an algebra mistake. So there's the graph. The red sections here are the portions I've added on with this next section. The equations are here again. If we look carefully, there's a little bit of change in the slope there. There's a little bit of a change in the slope there. Other than that, there's nothing real dramatic in this picture. Our free body diagram had the 118.1. We had the 200. We had FT and FR, and FT and FR vary as a function of x. Our next section, we add this reaction force of 131.9. My triangle triangle and rectangle loading that I had before, where I was calculating for any value of x, I get a rectangle portion and a triangle portion. Those equations haven't changed, and I can just kind of keep on going. And all I really need to do at this point is add this additional upwards direction force and whatever moment it causes to my existing equations. So if I took my previous equation for my shear force, V equals 2x squared minus 60x plus 318.1, and I just need to add the upwards force of 131.9, and I've got it with very minimal math. I could add those numbers together, but I'm not going to right now. Same with the moment. My previous equation, 0.6667 x cubed minus 30x squared plus 318.1 x minus 666.67. And I just need to add the moment caused by this reaction force, which is at 131.9 times this distance here from the end. So I'm going to say plus 131.9 times that distance, which is just x minus 12. And that gives me the equation that I need for our reaction forces for this section, where x is between that 12 and 15, which is a section after that force is applied. And there's our graph. I have the equations here in the same form that I wrote them on the previous page. And we'll notice that in the shear diagram, we have a discontinuity here equal to that 131.9. So the shear force goes from a negative value to a positive value. And in the moment diagram, we see that the slope of the moment changed from negative to positive. And as we get out towards the end, they both taper off to zero like we'd expect. And that's, a good check on our whole process here. Did I get to zero at the end? Because if I didn't, then I made a mistake somewhere along the way. And finally, we have the little bit tagging on the end. And I can just look at that by inspection. I see there's no loads on it, there's no reaction forces, there's no nothing. So my shear and moment aren't going to be changing at all. They're already at zero when it gets to that point at 15 meters. So for that last 2 meters, our V is equal to zero and our M equals zero. And that's all we really need. We can just continue those lines on over here equal to zero and don't have to do any math at all. And that wraps it up for today. I hope you found this useful, and we'll see you on the flip side.